right, everybody. In this video, what we're going to do is we're really going to focus on the pumping lemma for context-free languages. But we're going to do that in kind of a roundabout way. I want to talk about the languages that we know so far. We know about regular languages, we know about context-free languages, and we know that there are some things outside of both of those. The Venn diagram for this is shown on the right. And I like to talk about something called Titus Classification that is a useful feature of talking about these languages. A language could be a regular language, and we can prove that by drawing an NFA, a DFA, or a regular expression for it. But a language might also be context-free and regular, which we could still prove using a DFA, NFA, or regular expression. But a language could be context-free and not regular, which is this yellow ring in this Venn diagram. If it is context-free and not regular, we could prove that by proving it's not regular using pumping lemma or closure or something like that. And then we prove it's context-free by drawing a context-free grammar or a PDA or something like that for it. Lastly, the last ring here, this gray ring, is anything else. So it could be that it's not context-free, and we can prove it's not context-free, and generally we do that with the pumping lemma for context-free languages. There might be a way to use closure as well. It turns out that this big circle definitely encompasses all languages, including context-free and regular languages. But this Titus classification that I'm talking about is I want to take a language and put it nestled into kind of the deepest ring that I can. So if that language is in here, then I just want to prove that it's regular and be done. If that language is here, I want to prove that it's not regular, but it's context-free, because that's the Titus classification we have. If it's out here, then I just want to prove it's not context-free. Now, as we learn more classifications of languages, we might improve how many we can do this on. So here's language number one. Language number one is a language with a number of ABs followed by the exact same number of ABs. So a language like ABAB, or a string like ABAB. It could be ABAB followed by ABAB. And you could write this language like something like this, AB to the N followed by AB to the N. And whenever you have the exact same symbol followed by the exact same symbol like this looks a little bit context-free, but I can prove it's not by showing you a regular expression that does the exact same thing for all strings. This could include epsilon as well. So it turns out this is regular, and I've proved it's regular by showing a regular expression for it. So let's do a language whose Titus classification is context-free. So how about we take this AB followed by the exact same number of ABs, and we switch the order. So what if it's ABs followed by BAs? And the fact that these aren't the same symbol changes this AB to the N nature to be something that we kind of have to be careful with, right? So how do we prove this isn't regular? So you would take the pumping lemma for regular languages. You would pick a string like S equals AB to the P, BA to the P. You would say Y has to come from the AB portion. You know that if it includes just an A or just a B, that it's going to be broken. But the catch is there some clever way that we could delete A's and B's here to make it work? And we'd have to show that there's no possible choice for Y that makes this work. And indeed, there shouldn't be, assuming I have this correctly. In order to show that it is a context-free language, what we need to do is provide a grammar or a PDA for this. I think the easiest way would be to provide a grammar. And that grammar looks simply like this, where the ABs are always matched with the BAs, and that's it. So we've proven that it's context-free. I've kind of sketched out very, very broadly what a proof for that it's not a regular language might look like. And that would show that the Titus classification of this language, if you get both of these completely done, is context-free. All right, so this last one I'm going to spend a little more time with because I really want to focus on the pumping lemma for not context-free languages the most. What if we pick a language which is some number of A's followed by some number of an equal number of B's followed by some number of C's followed by an equal number of D's and E's in order, something like this. And this language is not context-free, and I want to show you how we prove it which is a little different than how we would prove it in the regular case. So this would be our third bubble. This is the not context-free bubble, and I want to use the pumping lemma for context-free languages to prove that it is not context-free. Now, the pumping lemma for context-free languages says that if it is context-free, there is some pumping length, and that any string of at least that pumping length has to have this following quality. The quality is that the string can be broken up um, into 5 pieces. Okay, so we usually call this string S1. Those 5 pieces are something like U, V, X, Y, Z. And the rule is that there has to be some V and Y. So either V or Y is not empty. Within P symbols, so the length between V and Y, including V and Y, um, is constrained to the length P. There has to be some place in any string that we get that's of length at least P, where if we break the string up into the appropriate pieces, there is some V and Y, and those V and Y, including what's in them, are not more than P apart, such that we can take the V and Y out, or we can add the V and Y in as many times as we want. So we have U, VI, X, Y, I, Z for all I. So we can either take it out, you can only take it out once, and you're left with whatever's left over after you take the V and Y out, or you can add it in as many times as you want to produce new strings that have to be in the language. Now, you don't have to produce all strings in the language this way, you just have to produce some. Okay, so part of the key to using the pumping lemma to show that languages are not context free is finding the right string that allows us to do these things. Sometimes it's really easy. In this case, it's kind of an easier one because it's kind of the default string that you would think of. Sometimes it's hard. So what is that string? S1 in this particular case is A to the P, B to the P, C to the P, D to the P, E to the P. And this is the string that I would always start with to see if I could break the pumping lemma, because the question is kind of written in this way where you have an equal number of things. That makes it easy. The full proof, you have to write a few things, like you're going to assume L3 is context free and obeys the context tree. It obeys the pumping lemma for context free languages. So we produce a string of length at least P, and we know in this string that the A's and B's have to be equal, and the C, D's, and E's have to be equal, right? And this is the default string I would pick. It would be kind of easy, right? And we come here and we say, hey, if we pick V and Y to be over here, it could reach 2 of these symbols, but not all 3, because the maximum length is P. So like it couldn't reach C and E at the same time. Therefore, pumping down breaks it, because I'd either remove 2 of the symbols or 1 of the symbols without removing the other 2. The problem is there is a V and a Y in this string that works. If I pick V to be the last A and Y to be the last B, I can remove those and stay in the language. Or I can add them and stay in the language. So it turns out this string obeys the pumping lemma for context-free languages because there is some choice for V and Y that matches all of these rules, where they're not empty, they're within P symbols of each other. In fact, they're right next to each other. The P here, the number of symbols next to each other is only 2. And I can remove it or add it in as many times as I want and stay in the language. So you have to be careful of this. So let's try a different string. This string doesn't work, right? So we'll draw next to it. Let's try another string. What if we delete the A's and B's? They seem to be a problem. And we'll write C to the P, D to the P, E to the P. Is this a string in the language? Let's come back up here to the language. It has an equal number of A's and B's. None is equal. And it has an equal number of C's, D's, and E's. This is better, right? We know that the length of VXY has to be less than or equal to P. So there's no way for V and Y to include all 3 of these symbols, C, D, and E. It's not possible. There's no way for V and Y to include all of these. And because there's no way for V and Y to include all these, when we pump down, S0 removes some of these 3, but not all 3. And since we know that the language consists of an equal number of C's, D's, and E's, removing some is not as good. It's not good enough to stay in the language. So S0 is not in the language. No matter what we choose, for V and Y, it could never include all three of these symbols. And therefore, there's no way that S0 could ever be in the language. And you have to consider all possibilities. And because there's no way, then by pumping down, we've proven that this language couldn't have possibly been context free, that our assumption was wrong, right? Our assumption was wrong. Now, this one works differently than the pumping lemma for context free languages, and it works differently because there's this sliding window idea, right? Where I can't just look at the first P symbols in this case. I have to look at any window of possible P symbols and make it work. And generally, what that usually boils down to is finding some place where I have to remove something, but I can't reach, right? So I can't reach the E's if V has some C's in it. And I know that V and Y would have to have C, D, and E in it because they all have to be equal. But you do have to be careful that you're not too anxious to look for this solution, that you don't make this mistake where you have to be careful not to make this mistake where, hey, V and Y actually do work in this situation. You have to be careful of that because this part of the language is rather context free. And that's what the pumping lemma is finding. It's finding this loop that you can loop over. Now, this part is not. And so I just clues a cleverer string, a string that's more clever that negates or eliminates or does not include that context free part so that I know I can pump down and break this language. Okay, we're over our 10-minute mark, so I'm going to end it there. This is Titus Classification. Your language can either be regular. By Titus Classification, it could be context free and not regular, although we know all regular languages are context free. Or it could be in the set of all languages, in which case the Titus Classification that we're looking for, like this dot here, these dots out here, is not context free. So languages right now for us are going to exist in one of these three rings, either the gray ring, which is not context free, the yellow ring, which is context free but not regular, or the red circle, which is regular. And all regular languages are context free, and all context free languages belong in the set of all languages. And so this is our Venn diagram. All right, that's it. Hopefully this gives you some extra stuff to work on the pumping lemma for context free languages. We'll let you go. See you next time. Bye.